Okay guys, so we're going to go over Unit 5 Standard 3. Now Unit 5 Standard 3 is linked to Standard 2 in the sense that we have both, we have to know the atomic structure in order to understand how charges work. Now when you have multiple charges, right, so if we gain a positive charge, we lost electrons, we can analyze how that actual charge produces an electric field. Okay, so we're going to call these point charges. So let's say this is my positive charge. That's a point charge. Okay, positive point charge. Each positive point charge produces an electric field. Now, field lines, we kind of went over this if you could recall. Field lines always point out of a positive point charge. Okay, so any object that is positive and that is charged, it will have field lines. These field lines, if it's positive, it's going to point away, right? So if you have a positive charge, the field will point away. Now, if we have a negative charge, so let's say we gain electrons and we have a negative charge, these field lines are going to point towards the actual point charge. Okay. Now, we know that if we have a positive and a negative charge, they're close to each other, they are going to want to attract. So now this is how they essentially interact. Okay, so the interaction of two electric fields. Now, the positive point charge will produce an electric field that pushes those electric lines away from the charge. A negative charge will pull those electric field lines. Now, when we get them close together, this is essentially how they look. So we have the positive charge pushing those electric field lines away, right? They push away from the actual point charge. Now, if we get a negative point charge close to those, what occurs is that the lines that are coming out of the positive point charge go into the actual negative point charge. So you'll see something like this. Now this is due to the fact that, and if we keep this going, it's going to come around, kind of go back into there. This is due to the fact that a positive and a negative always attract. Now, let's say what if we have a negative and negative or positive and positive. So if we have two positive charges next to each other, now positive point charges will have field lines that point away. So if we have these field lines that are pointing away from the actual charge, what occurs when these two come close together is that they repel off one another. Right? They do not want to go into one another. So you'll have these two lines that are pushing off of each other. Now, the closer these two objects are, the more field lines are going to interact, and essentially they will cause a strong force. Okay, so that's how these field lines work. Now they just push off of each other. The closer these two lines are, the closer these two charges are, the larger force because of the more field lines that are interacting. Now, that's if it's a positive, right? They all push away towards each other. Now, let's say if we have two negatives. So I'm going to erase this one here. Let's say we have two negatives next to one another. So we have a negative charge and a negative charge. Now we know that those lines are going to point towards the negative charge. So here we have these lines pointing towards them. Okay. Now when they get close to one another, you're going to see that interaction occur. Now the interaction that occurs is very similar to the positive point charges, where these two lines are still going to point off one another, but instead of the lines pushing off or going away from the point charge, they actually go into the negative charge. So these lines go into that negative charge, and again, the closer you get these two negative charges, the more force you're going to feel. The more lines that will interact, the closer these will feel. Now, this is essentially how you can determine Coulomb's law, right? So Coulomb's law is based off of the electric field line. So if you remember Coulomb's law, the equation was force of electrostatics is equal to K times Q1 times Q2 all over distance squared. So what this means, okay, what this means is that if you have two charges next to each other, the closer they are, the more force that they will feel. Right? So if we write this in words, we can say that the charges are directly related to the force of electrostatics. So what that means? What that means is, let's say we have Q1 as one of our charges. If the charge goes up, so if Q goes up, Fe will also go up. They're directly related. So if Q goes up by 2, Fe will also go up by 2. Okay. Now, if it goes down, then also force of electrostatic also goes down. So if Q goes down by 2, Fe also goes down by 2, so on and so forth. And that's how this essentially works. Now, we also have to take into consideration the distance. So up here, right, we said the closer that these two are, the more electric field lines will interact. The farther they are, the least they interact. So the closer they are, our force will go up. Right, so let me draw it down here. So now let's talk about distance. So distance. Okay. So now distance has an inverse relationship with force. So what that means is that force of electrostatics, let's go ahead and rewrite this. So force of electrostatics is inversely proportional to the square of distance. So if it goes down to this here. So our distance squared, if our distance goes up by 2, then our force is going to go up by that factor, right? So it's inversely proportional. So as distance gets closer, so if distance goes down, then force goes up. Right? So definition here, and then here's kind of our relationship. So if distance goes down, the force goes up. Now if distance goes up, vice versa, right? So if distance goes up, then force goes down. So distance going up, that means that the two charges are getting farther away. Distance going down, those two charges are getting closer together. Now, what does that square have to do with anything? Okay, let's figure this out. So distance, if we have, let's say distance went up by 3. So we know that the force, if the distance gets farther, the force has to go down. So how much does the force go down by? Well, if distance goes up by 3, we have to take the square factor of that. So 3 squared is 9. Our force of electrostatics will go down by 9. Okay, so it's going to be 1/9 the amount, and x is just the amount. So let's say distance goes down by 4. Okay, well the force of electrostatics is going to go up. That we know, because they're getting closer. But how much is it going to go up by? Well, what's 4 squared? The square is the factor that it goes up by, right? The square of the distance. So if the distance is 4, we square the 4. Fe is going to go up by 16. Let me rewrite that because that looks sloppy. 16. Alright, good. Alright, so let's go ahead and see how this works when we calculate it. Okay, so all of these problems, we're always finding knowns and unknowns. That's from the very beginning, we've always done that. So, knowns and unknowns, so a negative charge of negative 3.0 times 10 to the negative 6 and a negative charge of negative 5.0 times 10 to the negative 6 are separated by 0.15 meters. What is the electrostatic force between them? This should say force. Is this repulsive or attractive? Well, we can answer this second question right now. Is it repulsive or attractive? Well, we have a negative charge and a negative charge. So we know that two negatives will be repulsive. They will repel. Alright, so let's go ahead and start a math problem. So knowns, we know Q1 is equal to negative 3.0 times 10 to the negative 6. Q2 is equal to negative 5.0 times 10 to the negative 6. We know that K will equal 9.0 times 10 to the 9th. And then there's one more known that we have. It's our distance is equal to 0.15 meters. Good. There's our knowns. Those are all of our knowns, and what we're trying to find is the force of electrostatics. What is that? Now, if you remember the equation, Fe is equal to K times Q1 times Q2 all over distance squared. So let's go ahead and plug this into our calculator now. Plug in our knowns and unknowns. Let's not use a calculator just yet. Alright, so plugging in our knowns and unknowns for this, and I'll just put it right below it. Just put this right below it. We have Fe is equal to 9.0 times 10 to the 9th times negative 3.0 times 10 to the negative 6 times negative 5.0 times 10 to the negative 6. And I kind of ran out of space, but this will be times 10 to the negative 6. This is all divided by 0.15 squared. Okay, so drawing this over here, okay, again, what we do is we multiply the top, multiply the bottom, simplify it, get one fraction, then we can divide it. So Fe, if we multiply the top, again, type it in as you see it in the calculator. So parentheses 9.0 times 10, caret 9, parentheses, close parentheses, open parentheses, negative 3.0 times 10 to the negative 6, close parentheses, open parentheses, and then at the end you'll also have an open parentheses there. When you type that out, what you get is a 0.135 divided by 0.0225. Now, when you divide these two numbers, what you get is 6. Okay, so 6 newtons is your force of electrostatics at the end. All right, now let's go on and move on to the second problem. So now this problem asks us for force. This problem is going to ask us for charge. So there's a different way of solving this problem, and we're going to go over it right now. So again, we do the same thing we did in the other one. We got to find our knowns and unknowns. So finding our knowns, we know that K is going to be 9.0 times 10 to the 9th. That always is the same when we're working with charges. Now, the force of electrostatics is 9.0 newtons. Q1 is equal to a negative 0.0005, and then the distance is equal to 10 meters. What we're trying to find is Q2. Okay, so from here, what we're trying to find is that second charge. So again, we work with our equation. So Fe is equal to K times Q1 times Q2 divided by distance squared. Now, here, it's just plugging in our knowns and unknowns. So we know that Fe is 9.0 newtons is equal to K, which is 9.0 times 10 to the 9th, times Q1, which is 0.0005, times Q2, which we don't know what it is, that's what we're trying to find, divided by distance squared, so 10 squared. Now, again, we're going to want to simplify the top and simplify the bottom. So 9.0 times 10 to the 9th times 0.005, you'll get to be 4,500,000 divided by 100. Okay, so now simplifying this, that's just this problem here. Okay, now Q2 is still part of this problem, so it's 4,500,000 times Q2. Okay, so let's put this back together because we still have force here and then we still have this chunk there. So force is 9.0